Okay, so we want to solve this single source shortest path problem, okay? And it turned out that, in particular, we are going to introduce two algorithms in this class, today and the next class, okay? One is called the Bellman-Ford algorithm, which works for any weighted graph, okay? And the time complexity is V times E, okay? And the other is called the Dijkstra algorithm, which is more efficient, has better time complexity, but it only works for graphs with positive edge weights, so it doesn't handle negative weights, okay? But graph with positive edge weights is probably most common type of weighted graph in applications, okay? So today we're going to talk about the Bellman-Ford algorithm. But it turned out that both algorithms share something in common. Essentially, both of them are going to rely on a so-called update operation. So what this update operation essentially helps us to keep track of the shortest path distance estimate. Okay, so every time you update, we try to see, can we find a better way, a shorter path? Okay, that's what this update operation is going to help us. Okay, so both algorithms essentially will repeatedly perform this update operation, repeatedly try to see whether I can find a better, shorter path to go from the source to a specific node. Okay, till we cannot anymore. Okay, what differs is the order, what order they're going to perform this update operation. Okay, so now let's first talk about this update operation. All right, so from now on, for simplicity, I'm going to just use V and E to represent the cardinality of V and E in time complexity. Otherwise, it becomes very messy when I write it out. Okay, all right. Okay, as I said, the algorithm, both algorithms, we're going to try to maintain some estimate the shortest path. Okay, so let's fix our source nodes to be S. Okay, and our both algorithm will try to keep track of the shortest path that we found so far. Okay, you continue to explore the graph and then you maintain the shortest path you found so far. And this shortest path that you found so far is called estimate the shortest path. Okay, clearly the estimated shortest path has length larger than or equal to the two shortest paths. Okay, because this is what the shortest one you only found so far. Maybe you can find a better one later. Okay, and for graph node U, I'm going to use the U.est estimate to represent the length of this estimated shortest path from source to node U so far. Okay, so this is just the estimate distance so far from the source S to U that we have discovered so far. Okay, so this is what we want to maintain, this estimated shortest path and the estimated distances. Okay, and the algorithm on the high level at the beginning, the estimated shortest path distance would be infinity for everyone other than the source, because at the beginning we haven't found anything to go from S to them, okay, other than the source itself, which would give the distance to be 0 because I'm already there, okay? And then the algorithm would repeatedly perform this update operation we're going to talk about very soon, try to see whether we can find a better path to reach U for every node U. Okay, till then we deem that we're done. We already found the shortest path. Okay, and and through this update processes, okay, at any moment the estimated shortest path can only improve. You cannot be worse because you already found the shortest path so far. You only update it when you find a better one. So your estimate can only improve. Okay, and it's always at least the shortest path distance of the true one. Okay, and once it finds the correct distance, when it keeps decreasing till you found the correct distance, clearly it will stay that way and cannot change anymore because you cannot improve it further. It also, your algorithm cannot make it worse either. Okay. In our approach for every node U, we're going to maintain the current estimated shortest path distance from S to V. We're also going to maintain the predecessor along this estimated shortest path from S to U. Okay, so basically your algorithm so far found some paths going from S to U, and that path so far is the best path you found, okay? And you maintain the predecessor along that path, okay? All right. Okay, so here is this update operation, okay? On the high level, so the update is performed for an edge UV in the graph, okay? So suppose you have an edge U, V. I'm using direct graph as an example here, but it doesn't have to, it works both for directed and undirected, okay? So suppose you have this edge UV, and now I'm going to perform update on this edge UV in your graph, okay? So essentially, intuitively, what this update operation is doing is that, so suppose, so your source node is here. Your source node is here somewhere, okay? Now remember that at this point, you already found some estimated shortest path from S to V, okay? And let's say that you already have a predecessor along this estimated shortest path. Let's say call this one X, okay? So this blue one is so far the estimated shortest path from S to V, okay? And this is its predecessor, okay? The update operation essentially is asking, okay, can I find a better way to reach V taking U as the predecessor, okay? All right, so is U a better predecessor for V along some path, okay? So if there's a path going from S to U and then UV, that is shorter than this current best one, this blue one I found. If that answer is yes, then I'm going to update my predecessor from X to U, because now I found a better way to reach V, okay? And then I update the distance to be the one going from S to the new estimated, the new path length. Okay, so that's what it does, okay? I'm going to make it more concrete with example in a minute, okay? So let me just repeat what I said. So we said that, okay, I already know there's some path going from source S to, let's say that use current. This is use current predecessor. And then to V, okay? So I already have a path, which is from S to the X to V, where X is the current best, the predecessor along the best estimated path we found from S to V, okay? So now you ask, is the best way I can go from S to U and then from U to V, is this, if I do the best way going from S to U using my current estimate and then from U to V, is this path better? So is blue path better? Means shorter than green path. Again, the green path is the current estimated shortest path from S to V, okay? What's blue path? Blue path is the best way to go from S to U plus the edge UV. So this is another way to reach V, okay, which has U as its predecessor. So we ask, is this blue one better when so this is what the update edge UV is doing, okay? So is this blue one better? If the answer is yes, that means that I discovered a shorter path from S to V, which is through U, this blue one I discovered. So then we simply change V's predecessor from X to U, and then also update this estimated distance. Okay, all right. So algorithmically, what do we do? Algorithmically, we're doing the update on the on edge UV. I basically ask that what is the length of the green path? The length of the green path is simply the current estimate. So this is the length of green path, right? The green path is the current estimate. estimated the shortest path, and its length is simply what I currently estimate, v dot estimate. Okay, and what is the length of the blue path? The blue path is the best way to go from S to U plus the edge UV. So the length is best way go from S to U is U dot estimate. That's the best way so far we found going from S to U plus the edge UV, which will add the weight of UV. So this is same here, is simply the length of blue path. Okay, the blue path is the new one we just discovered. Okay, so we asked, is the blue one shorter? Okay, if yes, then we found a better way to go from S to V through U. So by going from S to U first and go from U to through edge UV. Okay, so we update. We say that now I update the shortest path estimate at V to be this new, the length of the blue path. Okay, so this is the length of blue path. We updated shortest path estimate to be length of blue path. And we also set U to be V's predecessor. Okay, if not, then we didn't find a new one, so we do nothing. Okay, that's it. Okay, questions? Okay, so here I'm using greater than or equal to. You can also just change this to be strictly greater than. It's actually cleaner that way. I'll update the slide later. Both are correct. Okay, all right. So yeah, so this is the same one that I'm showing. This is the blue path that I was just drawing. Okay, so let's look at an example before we give the implementation of this. Okay, let's say that this is a current configuration that I already discovered. S is the source node. Okay, and now for all these nodes, I already have some estimated shortest path, which are the numbers that are marked here. So the estimated shortest path to U1 is 7, to V is 10, to U2 is 4. Okay, and the red edges are the current predecessor for each of the nodes. So for example, to reach V, the current predecessor along the current estimated shortest path is edge U1 to V. Okay, same for U2 and so on. Okay, so if this is what we have, let's now consider, suppose now I perform update operation to U2V. Okay, so now I do update along this purple edge. Okay, all right, what does it mean? So we're going to do update along this purple edge. Okay, so now the V estimate right now is 10. That basically goes through from S to U1 and from U1 to V. Okay, it's because predecessor currently is V1. So currently my best shortest path is 10. Okay, but now since I'm doing update on this edge, I've now discovered through this edge, I discover new path. What is the new path? The new path is this blue one going from S first to U2 and then from U2 to V. Okay, so what is the length of this blue path? The length is U2 dot estimate, the best way to reach U2 plus the edge weight of U2V, which is 4 plus 2, which is 6. Okay, so now we see that the current estimate 10 is bigger than 6. Namely, I found a better way to go from S to V through U2, because this new way only takes length 6. Okay, as such, I'm going to update. I'm going to update my V dot estimate to be the new distance. And I'm going to update the predecessor for V to be U2 now. Okay, so that's what we do. So here is exactly what I just wrote. Because V estimate, the current estimate is bigger than the length of the new one that I found, that means we found a better way going through U2. So as such, I simply update the distance to be this new way, and my predecessor of V now is U2 now, because I found a new path going from S to to V through U2. U2 is my predecessor in this new better path. Okay, so this is what we have. Okay, so that's what the update is doing. That's all. Okay, if suppose that this is a configuration where before the update I change the number here. Okay, if this is what we have, then suppose we perform update operation on the same edge, U2V. Okay, now we notice that V dot estimate is 10, but the new blue path we found now is U2 dot estimate plus the weight of U2V now is 9 plus 2, which is 11. So what does this mean now? It means that, okay, you did find another way to reach V through U2, but this way is no better than what I already discovered. Okay, so you do nothing. You just can keep everything the same, do nothing as before. Okay, so this is what the update is doing, the two cases. Okay, all right, and to implement this, okay, we assume that globally in our algorithm we maintain, and you can take it as an array, or in Python we use a dictionary. But in general, you can assume that we have an array to store all the with one entry for each of the vertex, each of the node in the graph. Okay, so in Python you can use the dictionary, and also we also need to store the predecessor for every node. So this is dictionary of size V. This is also of size V. Okay, because it's one for every node. Okay, and suppose so the weight is a function which return the edge weight as a part of the input. Okay, so assume that we maintain this. This is to maintain the estimated shortest path distance. This is to maintain the predecessor. Okay, once we have this, here's the Python code for the update operation. So all of this are maintained, and now if we want to do update on edge UV, this is exactly what we said. We check, is this bigger than this blue? This is the length of the blue path that we talk about. Did we found a better path? And if the answer is yes, then I update the estimate to the length of the new path, and I change my predecessor to be this U. If I didn't find a better way, then we return false. We say that I didn't change anything. I didn't find a better way, and do nothing. That's it. Okay, all right. So the update operation here, we return true if we found a better path, and false otherwise. And meanwhile, inside the code, when we return true, we also update the estimate of shortest path and the predecessor. Okay, what's the time complexity of this? What do you think? Well, if we're just talking about update for one edge, then clearly these are all constant time operation. So the time complexity is simply constant, order of 1. Okay. Okay. Now, when we do an update operation, if we found a shorter path, is that the new path necessarily the shortest? Okay. So like in the previous, this example, when I perform update U2V, I found a better way to go from U2 to V. Is this necessarily the shortest path from S to V? Well, not necessarily so. It's just the best that so far we found. Later, as you continue to perform update and explore, you may find even better ones. Okay, so we might maybe later discover yet another shorter path going from S to U1 and then to V again. Okay, so this is not necessarily shortest path yet. Okay, now when do I know that we have the shortest path? Well, here's a theorem that will help us with that. Okay, so let's say that U and the V are all graph nodes. Okay, and suppose currently the estimate for U, let's say that I have U here and a V here. Okay, suppose at this point my estimate, the shortest path estimate for U is already correct. What does that mean? That means that I already somehow managed to find the shortest way to reach U. So this is already correct. This equals to the shortest path distance from S to U. So suppose that's the case. Okay, all right, that's condition A. Okay, suppose that indeed there is some shortest path that go from S to V that goes through where U is the predecessor. Okay, all right. In other words, suppose that the best way going from S to U plus this edge is indeed the shortest path to V. Okay, and we already get U correct. Then, under these two conditions, if I now perform update operation, then after that, V must get the correct shortest path distance as well. Okay, why? It's easy to see, because if I now perform the update, then afterwards, V dot estimate equal to U dot EST plus the weight of edge UV. But I already know that this is the shortest path. In other words, afterwards, I get the correct shortest path to V. Okay, all right. So this may sound a little bit confusing. What this is really saying is the following. Okay, it says that, so let's say that you have U to V. Okay, it says that if the shortest path to V has U as the predecessor, okay, then once I found the estimate to U correct, then by doing update UV, I can find the correct distance to V2. Okay, so this intuitively can help you to imagine how you're going to compute the shortest path now. Okay, so in other words, once I get my predecessor shortest path estimate right, then if I now do the update on this edge, I can get myself also correct. Okay, and once I get myself correct, whoever that had me as a predecessor in their shortest path, when I update the edge to them, I can get their shortest path estimate correct as well. Okay, so you will see shortly that the Bellman-Ford algorithm will basically leverage this idea. Okay, which we're going to talk about now.